Welcome! My name is Lisa, and today I'll be teaching you about the chemistry topic calorimetry. The book we'll be using is Chemistry, An Atom's First Approach by Susan Zumdahl and Stephen Zumdahl. Calorimetry has to do with quantifying, which means getting a numerical value, of the amount of heat that flows between two systems after a chemical reaction. Calorimetry is measured using the temperatures of two systems and relating that to energy. But different systems require more energy to raise the temperature by 1 degree Celsius. Because of this, we have something called a heat capacity for each material. And here is the formula for heat capacity. Heat capacity, C, is equal to the heat absorbed by the material divided by the increase in temperature. And if you want to take the heat capacity per gram of a substance, then that would be called the specific heat capacity, which is denoted S. If you want to know the specific heat capacity per mole of a substance, that's called the molar heat capacity. And by the way, the units of heat capacity are joules, which is the heat absorbed, per increase in temperature, which is in degrees Celsius. So the molar heat capacity would have units of joules per degree Celsius times mole. And this would be joules per degree Celsius times gram. So let's say the reaction happens inside the water solution in this styrofoam cup. There are three things that depend on how much energy is released by this reaction. The first is the temperature increase. The next one is the mass of the solution. The third is the specific heat capacity of the solution. The energy released by the reaction is going to equal two things. The energy absorbed by the solution, which is going to be the temperature that we measure. It's also going to equal the product of the three things that I just taught you guys. Even though I just talked about chemical reactions, the equation that we just derived can also help us find the final temperature when we mix two samples of water that are at different temperatures. They'll come to a certain temperature together in a certain amount of time. And the equation for the heat that is released from a chemical reaction into its water solution can be used for the same problem. I wrote down a type of problem on the board. Determine the final temperature when 32.2 grams of water at 14.9 degrees Celsius mixes with 32.2 grams of water at 46.8 degrees Celsius. Okay, so let's define our final temperature as the most common variable used, X. So our final temperature is going to be X, and this is what we're going to try to find. Okay, so we have two samples of water. One of them was at 14.9 degrees Celsius, and the other one was at 46.8 degrees Celsius. The final temperature is going to be in between these two. Doesn't that make sense? We observe that every day in real life. So if it's going to be between these two, that means it's going to be under 46.8 and it's going to be over 14.9. By how much? We don't know yet. We didn't start the problem. How does our heat equation that we derived earlier fit into this problem? Well, let's see. The heat lost by the sample of water with the greater temperature is going to be equal to the heat gained by the sample of water with a smaller temperature. And what was our equation that we derived? S times M times change in T is going to be the same on both sides. Even though the variables on each side are the same, we're going to have different values for each of them, for each side, hopefully, right? Because we don't want them to cancel. So what's S? Well, that would be 4.184, which is the specific heat capacity of water. You can look that up. And we're given 32.2 grams for each. So we know S and M for both sides. Now we don't know T for either side, and this is where they're going to differ. So X, our final temperature, we can look at this a lot easier if we put it on a number line. So we have this number line, and we have 46.8 degrees Celsius over here, and 14.9 degrees Celsius here, and we agreed that X was going to be somewhere in the middle of these two. So the change in temperature is going to be this here and this here. So the change in temperature for the heat lost would be this one, because 46.8 is right here. And this sample of water lost heat because X is here, less than. And the heat gained by the system is here because the 14.9 is right here, and it's gaining temperature to get to this final temperature X. So what does that mean? So this amount of degrees is equal to 46.8 minus X. Can you see that? 46.8 minus X is this amount of distance right here on the number line. And the heat gained is this delta T right here, which is going to be X minus 14.9 is this void. See that? So we understand the values of these two delta T's. 46.8 minus X, X minus 14.9 is going to be the amount in each of these. So now, we can put X minus 14.9 here, and 46.8 minus X here in the Q lost. Now we just plug in. Now, we know S is 4.184. That's the specific heat of water. You can look that up. Times the mass is 32.2. We got that from the problem. Times 46.8 minus X for the change in temperature in the Q lost. Opposite side. S is 4.184. M is 32.2. Because both of these samples of water happen to be the same amount of grams in the problem. And change in temperature is x minus 14.9. Now we can take a calculator to this. 4.184 times 32.2. And we get x equals 30.85 degrees about. Is that in between? 30.85 is in between 46.8 and 14.9 degrees Celsius. And that's our answer. And that's how you find the final temperature of a solution of water after you mix two samples of water with different temperatures. Hope you enjoyed. Thank you.